In this class, I will explain the concept of moment of inertia MI or second moment of area of a section. So, in the earlier classes, we have defined about the centroid. Now, here to define the moment of inertia of a section, I will consider a plane figure, that is two-dimensional figure. This is the plane figure, can be a rectangle, triangle, circle, whatever it is, two-dimensional. So this figure area A. I will consider an elemental area in this. So the elemental area I will take it as dA. Elemental area is dA. I will take the distance from the y-axis to this element area as x. Distance measured from y-axis is x, and the distance measured from x-axis I will take it as y. Now, if you write the moment of area dA about y-axis, that can be written as just like similar to moment of a force, which is nothing but magnitude of the force multiplied by the perpendicular distance of the line of action of the force from the point of consideration or the axis of the consideration. Here, moment of area is given by dA, that is the area, into distance of that area from y-axis, which is x. So, x into dA is the moment of area dA about y-axis. Suppose if I take the second moment of area, that means once again I have to take moment. Second moment of area dA about y-axis. So the first one is the first moment of area. This is second moment of area. Once again you have to multiply this by x. So dA into x. That means it is x square dA. X square dA is the second moment of area. This term, second moment of area, is also called as moment of inertia. Moment of inertia of the area dA above y-axis. Suppose if you want the total, that is moment of inertia of total area A about y-axis. This can be written as integral x square dA. So integral x square dA is the moment of the total area A about the y-axis. On similar lines, if you write the moment of inertia of area A about x-axis, if the distance is measured from x-axis, then it is integral y square dA. So this integral x square dA, moment of inertia about y-axis, can be written as Iyy, whereas this is Ixx. So what you can say here is Ixx can be defined as integral y square dA. Iyy can be defined as integral x square dA. So this is the concept of moment of inertia. This is very important because the value of moment of inertia of any section with respect to any axis, it governs the strength of that particular section against the external forces. For example, if Iy is very high, then it has got a higher strength. That is the meaning. The resistance to externally applied forces is more if we have I value more. So, and another thing is, this moment of inertia of a section varies with the axis of reference. That means about which axis we are going to consider, that we have to take, or about which point. For example, if I have an area like this area of course is A, and if I take the moment of inertia of this axis about y dash axis, moment of inertia of this area about y dash axis, then I have to take, for example, this dA is this. If I take this as x1, then y1 will be equal to integral x1 square dA. If I take some another axis, y2 axis, y2 axis. Then if I take the distance as x2, then I y2 will be integral x2 square dv. So like this, the value of moment of inertia section, it varies with the axis of reference about which we are going to consider the moment of inertia. So this is one concept. Now, if I take an axis which is perpendicular to both x and y axis, so I consider an axis which is perpendicular to both x and y axis, means it is z axis. So in the z direction, if I take like this, so this is x axis, this is y axis, origin. I will take another axis, z axis. So this z axis is perpendicular to xy plane. I can go like this. So if I take the area dA here, this is the area dA, this distance is y, this distance is x. If I join this to the origin, I will take this distance of r. So this r is the distance measured to this dA from this z axis. Now here I will take this term integral r square dA instead of x square dA and y square dA. I take integral r square dA. This is defined as moment of inertia of area about z axis, which is perpendicular to xy plane. That is, it is perpendicular to both x and y axis. Now, if you this is called as polar moment of inertia. Polar moment of inertia, that is IZZ. Now you know the relationship r square is equal to x square plus y square. From the Pythagoras theorem, you can write that. So if I integrate both sides with respect to dA, it will be something like this: integral x square dA plus integral y square dA. So this integral x square dA, we know that it is Iyy. So this is Iyy plus this integral y square dA is Ixx. That means, and this is Izz. So that means Izz is equal to Iyy plus Ixx. So this is a very important concept. This is called as perpendicular axis theorem, because z axis is perpendicular to both the x and y axis. This is called as perpendicular axis theorem. That means the polar moment of inertia or the moment of inertia of an area about an axis which is perpendicular to the plane of the area will be equal to the sum of the moments of inertia of the area taken about the two mutually perpendicular axes. So that is the perpendicular axis theorem. So Ixx plus Iyy is equal to Izz. So that is the perpendicular axis theorem. So you can write the perpendicular axis theorem in this manner. The statement you can write like this: the moment of inertia of an area about an axis, moment of inertia of an area about an axis perpendicular to its plane, moment of inertia of an area about an axis perpendicular to the plane. That means it is z axis. Plane is xy plane. So z axis is perpendicular to xy plane. This is called as polar moment of inertia. So this is also called as polar MI. So I am writing the statement of perpendicular axis theorem. Polar MI at any point O. Here I have taken point, this point O. So always when you are speaking about moment of inertia, it should be with respect to some point or axis. that is the point of reference, is equal to the sum of moments of inertia, is equal to the sum of moments of inertia, is equal to sum of moments of inertia about any two mutually perpendicular axes, about any two mutually perpendicular axis. Mutually perpendicular means here it is x-axis and y-y axis. So those two are mutually perpendicular and both of them are perpendicular to z-axis. Mutually perpendicular axis through the same point O and lying in the same plane. Through the same point O. So statement you have read correctly. Same point O and lying in the plane of the area. So this is the exact statement of perpendicular axis theorem statement. So state and prove perpendicular axis theorem if they ask her. So this is the statement and this is the proof. Proof is very simple. You have to draw this diagram and substitute for r square as x square plus y square. Integrate both sides with respect to a. So according by the definition of moment of inertia, so you will get the answer. So Izz is equal to Ixx plus Iyy, that is the perpendicular axis theorem. Now the next definition is radius of gyration. Radius of gyration denoted by k. The moment of inertia is denoted by I. Radius of gyration is denoted by k. Here also radius of gyration of any area is defined as, suppose if I write with respect to x-axis, it is written as kxx. It is nothing but square root of Ixx by a. So this is radius of gyration of area A with respect to x-axis. If you take with respect to y-axis, kyy is written as Iyy by a. And if you take with respect to zz, kzz, so this is called as polar radius of gyration. So this is given by square root of Izz divided by e. So please note that I will write the units now, SI units. So I is expressed in, moment of inertia is expressed in millimeter power 4 because you can see that it is either x square d or y square dA. X square means it is millimeter square. Area means it is also millimeter square. So millimeter square multiplied by millimeter square is millimeter power 4. Area will be in millimeter square. Therefore, k will be in root of I by a means it is millimeter power 4 by millimeter square under root which is millimeter. So k is expressed in millimeter or centimeter or meter. So whereas moment of inertia is expressed in millimeter power 4 or centimeter power 4 or meter power 4. Now this is how we can define radius of gyration. Once you get the value of moment of inertia, you can always find out the value of radius of gyration from the value of moment of inertia and the area of the section like this. Now there is one more theorem of moment of inertia which is called as parallel axis theorem. That is also very important. So there are two important theorems. One is perpendicular axis theorem, second one is parallel axis theorem. So state and prove parallel axis theorem. So like that we can ask in the examination. So we will see now what is the statement of parallel axis theorem and how to prove that. So here I will write the statement. So statement we have to write correctly and clearly. So parallel axis theorem. Parallel axis theorem. So according to this, I have an area A here. So this is the area A, total area A, any planar area. I will locate the centroid of this area. G may be somewhere here. So G is the centroid here. G is the centroid of that area. and I will write the axis passing through this D, horizontal axis passing through this D. So this dx can be taken as horizontal centroidal axis because it is passing through the centroid and it is horizontal. So it is horizontal centroidal axis dx. Now we will take another axis which is parallel to this dx axis, which I will take it as AB. So AB is an axis parallel to dx axis at a distance yc. So that means the distance between these two is yc. Distance between these two parallel axes is yc. Now, if this is the thing, this parallel axis theorem is used to find the moment of inertia of any axis which is parallel to centroidal axis. So that means here, suppose if I want the IAB here. So what is IAB? MI, moment of inertia of area A with respect to axis AB. IGX is moment of inertia of area A with respect to axis dx. Now if I want, I know, let us say I know IGX. If you know IGX, you can find out the IAB using this parallel axis theorem. It states like this: IAB is equal to IGX plus A into yc square. So this is the parallel axis theorem. Very important statement. So IAB, that is moment of inertia of this any area with respect to an axis which is parallel to centroidal axis, is equal to IGX, moment of inertia of the area with respect to centroidal axis, plus area of that section multiplied by the distance between the two axes square. So if you write the statement of this, so I can write like this: moment of inertia about any axis in the plane of an area. Statement can be written like this: moment of inertia of any axis in the plane of area. In the plane of area, so it is in this plane only. Moment of inertia about any axis in the plane of moment of inertia about any axis in the plane of area of an area is equal to the sum of plane of an area is equal to, I am writing the wordings of this equation: moment of inertia about any axis means here it is area in the plane of an area is equal to sum means this plus sign, sum of moment of inertia of the area about its centroidal axis, or you can write parallel centroidal axis, about parallel centroidal axis. That means parallel centroidal axis means it is this one, IDX. I can write dx parallel because AB and dx are parallel centroidal axis, and the product of the area and square of the distance between the two axes, and the product, that is this one, and the product of the area and the square of the distance between the two parallel axes. This is the statement. Square means yc square. So yc is the distance. So that means it is yc square I have to take. Product of the area y it is d. So that means it is sum of, it is plus the sum of these two. One is igx, that is the moment of inertia of the area about parallel sectional axis, that is igx, plus product of the area and square of the distance is a into yc. So this is the statement of parallel axis theorem. Now we can prove this because in the examination they can ask state and prove parallel axis theorem. For that, what this same figure I am going to use, I will consider an elemental area here. dA is the elemental area at a distance y from this gx axis. So a proof is like this. Consider an elemental area dA at a distance y from gx axis. So according to the definition of moment of inertia, what I will do here is IAB. IAB is equal to integral the distance of this dA from AB axis. I have to take, which is nothing but y plus yc. Y plus yc is the distance. So I have to take distance square, y plus yc square dA. This is according to the definition of moment of inertia. Because we know that ixx is integral y square dA, iyy is integral x square dA. Here I am taking IAB, distance of this elemental area from AB axis is y plus yc. So if I try to simplify this, integral a plus b whole square formula I will use y square plus yc square plus 2y into yc into dA. Just I have used the formula a plus b whole square. Now I can separate the terms. Integral y square dA plus integral yc square dA plus integral 2y yc dA. This is what I am going to get. Now integral y square dA, according to the definition of moment of inertia, it is igx. Ixx means it is igx here because I have taken the horizontal axis as central axis as igx here. So this becomes igx. So igx first term becomes igx plus here yc is constant. You can take it outside. So it becomes yc square. I can take outside into integral dA. Then plus here I will take 2yc constant into integral ydA. 2 into yc is constant. Now here we have to understand one thing here. What is the meaning of this integral y dA? That I have to write now. So now what I will do here is, this becomes now IAB is equal to IBX plus yc square into integral dA is dA itself plus 2yc into integral ydA. Now let me see what is this integral ydA. So integral ydA, according to definition of centroid, y bar is integral ydA by a or integral d. So like that we can write. So integral d like this. Or in other words, integral ydA is equal to y bar into integral d. So I can write like this. Now if I use this concept here, the meaning of this is y bar here becomes 0 here. The reason is I have taken this axis as x-axis and centroid lies on this axis itself. Therefore, distance of centroid from x-axis is y bar. According to the definition of centroid, distance of centroid from x-axis is y bar, from y-axis is x bar. Now here, if you observe the diagram, since I have taken the centroid of this axis itself, that itself it acts as x-axis. So y bar is equal to 0. This is because This is because y bar is distance of g from dx axis. Since d lies on dx axis, the distance becomes 0. So therefore y bar is 0. Once y bar is 0, so this integral y dA becomes 0 here. So this becomes 0 here. Very important step. So integral y dA becomes 0. When integral y dA becomes 0, this term becomes 0. So therefore we are left with only two terms. So IAB is equal to IGX. You can see here IAB is equal to IGX plus A into YC square. So this is the parallel axis theorem. So statement proves parallel axis theorem. So we have to write the statement, you have to draw a diagram and simple derivation in 3 steps where this concept is very important. So once you take 0 here, so you are going to get IAB is equal to IGX plus A into YC square. So this parallel axis theorem is used to find, so this is the parallel axis theorem. This is used to find the moment of inertia. For example, I will take a rectangular section. I know centroid is here. This is your x-axis. And if I want this is your AB, suppose let us say, if total is D, if total is depth is D, then this becomes D by 2 because centroid lies at the geometrical center. So AB is this axis. Suppose here, if I want IAB, moment of inertia of this rectangle, area of this rectangle is A. I can, if I know IGX, I can find out using this formula. Here A is B into B. For the rectangle, area is B into B. For this YC is the distance between these two parallel axes, which is D by 2. So once you know IGX, you can find out IAB. So if you know the moment of inertia of any section above its centroidal axis like Gx, you can always find out the moment of inertia of that area above an axis which is parallel to that centroidal axis using this parallel axis theorem. Only thing you should know the distance between these two and the area of the section, and vice versa. If you know IAB also, you can find out IGX. So IGX, if you know about the parallel axis, IAB value if you know, IAB minus A into YC square gives the value of IGX. So anything, either this or this may be unknown in a given problem. So you can find out using this parallel axis theorem.